Okay. Hi guys. I don't know. Like maybe I'm live. I just need to check once. Mm, like how to check if I'm live? No. Okay, I'm live actually. I got a notification as well on my other channel. Yes, I can see. I'll just add a comment. Hi guys. So I'll just start with what I was already doing on my other channel. Okay, let's just see if I can. Yeah, I can give a love. Uh, so sign. Okay, I'll sign it later. Can I see the? Okay, so let's start with what I was already doing. So I'm currently reading the system design resources, which is part of the interview ready GitHub channel. This is basically the channel run by God of Dev, God of Sign, which you can see. Okay, so his GitHub name is Going Parrot. We can see here. So I'll just start with one resource added like each daily, and then as time progresses, I can start with two or maybe more resources, right? More readings daily. For now, I just want to be more consistent rather than focusing on the quantity of things I am doing because I want to do a lot of things. Let's start with the system design resources. So table of contents, first point, or the first topic which we are going to cover today is video processing. Let's start with it. So under video processing, we have a bunch of topics: transcoding videos at scale, Facebook video broadcasting, Netflix video encoding at scale, Netflix short based encoding. So first one is based on that YouTube algorithm, how they transcode videos and when they transcode videos. Okay, second is related to Facebook video broadcasting. Third one is Netflix video encoding at scale. The fourth one is Netflix short based encoding. So I'll just start with the transcoding videos at scale. Okay, so transcoding, how we serve videos at scale. So this is related to YouTube transcoding. So there are a bunch of other platforms where we can do live streaming. One popular live streaming platform which I've heard of is Twitch. There are a bunch of others as well. But in this, but today we will be covering the YouTube transcoding videos at scale. So with the rise of social networks and mobile, videos have become one of the most dominant content types. So I can't deny that. I'm right, and I'm 100% with you. Video studies show that user engagement is the highest with videos which appeal to the new era of consumers because it is always easy when we are seeing things practically visually. So visual right, memory is far greater, right? Rather than memorizing something or just reading it, which you are doing it right now, which you are doing correct now. So also there is an inherent expectation that the content consumed is not only available instantly, but also that there is continuity as user jumps from one device to another, right? So it's not only about right the content that is consumed and how available it is, how instant availability to be get, but right it also about it's also about like what are the things we need to do, especially when a user is moving from or jumping from one device to another. So let's say he is watching the same video. He may be watching same video in Android, um, right, an iOS device, right, or maybe a MacBook. So depending on the different platforms and devices, both in terms of right system software and hardware, we have to have a consistent like algorithm which will enable us to right or everyone to watch the videos at large. So streaming and playing videos over the internet is far more complicated than it seems. Rather than downloading the videos and then right running it or playing it on your local or the native application, right? So the various problems with serving and playing videos are, so let's go through the list of challenges that we face right when running such a big application like YouTube at scale. So video file sizes typically range between a few hundred megabytes to multiple gigabytes. So this makes it really difficult to download the whole video and then play it, which we normally do when we do off where we do when we do offline downloading and then watch a movie or any video sort of, right? So the concept or the idea of first downloading the whole video, which may be like multiple gigabytes in size, and then playing it is like nonsense because the user will have to wait a lot, and there may have to so there won't be buffering for sure, but the user have to wait a lot before he can even start playing the first previewing the video, which isn't what a YouTube is made for. So users also may not want to watch the entire video, so that makes sense because most of the videos, most of the users first preview the videos, and if they like it, they go with the entire video, and if they're not, then they will just skip it, right, and move on to the next. Maybe just come out or log out of the YouTube application, right? So, but just some parts, right? It does not make sense to wait for the entire file to download and then play it. Native support for playing videos is very limited, right? For example, Windows does not support MOV files. Apple devices does not support WMB files. So native support for playing videos is very limited, which is very true. And for that, we do something called video transcoding, which we'll read more later. And third point is like videos with the same container type. MP4, MOV, WMB, etc. can have different codecs, and not all codecs can be played on all devices, right? So high resolution videos are not suitable for fast streaming on mobile devices with limited internet connection, right? Limited and right slow internet. So that is not enough. So high resolution videos are not suitable for fast streaming. Very true. So the solution to their problems, right, is video transcoding, which is basically the process of converting a video file from one format to another and making it viewable, right, across platforms. In this case, we're talking about the software platforms, right, and devices, which are the hardware things. So there are two types of streaming options we can have, like adaptive bitrate and then static bitrate. So the adaptive bitrate video experience is superior, right, to a static bitrate because the video stream can be manipulated. So because the video stream can be adjusted, Okay. Okay. This is uh, like how to see it. Just wait a minute. There you go. So when I'm like streaming, like it's depending on in my internet connection. Mm, we can change the type
Just
or
wait a
the
minute.
video quality based on the level of the capacity of the internet speed you have. But it's done automatically by the YouTube algorithm.
There you go. So when I'm like streaming, like it's depending on in my internet connection. Mm, we can change the type. Just wait a minute.
Video quality Okay, let's go back to what I was already doing. So the solution to the other problem. So what was the problem? First problem was the size of the right video could be too big. So it's not a probable solution or right a proper solution to first download it, the whole video and then play. Right. Second problem was native support because there are right videos of of multiple extensions and all the right and they may not be supported in different native devices like Windows. We have Apple devices, we have Macs, right? Third one could be like videos with the same container type can have different codecs. We'll talk about it. And not all codecs can be played on all devices. And also like high resolution videos are not suitable for fast streaming on mobile devices which has like limited bandwidth. So the solution to the problem is video transcoding, which is basically the process of converting a video file from one format to another and making it viewable across different platforms and devices. So there are two types of streaming options: adaptive bitrate and static bitrate. So in adaptive bitrate, the video experience and the relative bitrate video experience is superior to a static bitrate because the video stream can be adjusted, or the quality of the streaming can be adjusted based on the internet connectivity and the bandwidth available to the clients. So the clients is based on the client's availability, available network speed to avoid buffering or interruption in the playback. So the other format that we were interested um, in is called the HTTP livestream or HLS, which has emerged as the standard in adaptive bitrate video. So the next step was to decide when we should transfer videos. So we considered two options: transfer videos asynchronously after they have been uploaded, right? So this is required to transfer all the incoming videos, including those that may never be previewed in the future, and require a SLA. So what is SLA? SLA is basically a service level agreement, which is done between a client and our service provider. Alright, so that documents so it basically contains the document that service that accounts for the services that the provider will furnish and define the service standards the provider is obligated to. So the other format that we were interested in is HTTP HLS or HTTP live stream. So the next step was to decide at which when we should transfer videos. We consider two options. When, so that's very important. So we transfer videos asynchronously after they have been uploaded by the publishers. This will require us to transfer all the videos that are that are undercoming, that are incoming videos, including those that will never be previewed in the future, and would require SLA drive architecture to find the right balance between the preview availability and cost. And second one is like transcode on the fly. When a user hits a play, this would reduce the amount of video. So transcode video on the fly. So do it when the transcode the video only when user hits the play button. So this will reduce the amount of data that needs or video, amount of video that needs to be transcoded. But video transcoding of large files can be slow, so it would require high-end machines or even expensive GPUs to meet user expectations, which is not a prior solution. Our data team helped us to get the answers there. It turns out that 20% of all our data is video, and 40% of our users use mobile devices. So we started looking at how they shared, previewed, and streamed videos. We found that the majority of users previewed videos at least a few hours after upload. That's what I generally do, so that this gives us enough room to transfer the videos asynchronously. So most of the views come after 5 days. So you could do it's not right. It's not compulsory to transfer the videos right after it's uploaded uh, by the like publisher. What we could do, like there is a small chunk, there is a big chunk of right viewers that watch the videos probably after 5 days, but there are still people who watch it within less than 0 minutes, between 0 and 1, 0 to 10 minutes, 10 minutes to 1 hour, 1 hour to 12 hour, 12 hour to 1 day, 1 day to 5 day. For this segment of people or the viewers, what we do, we use the second option, which is to transfer the videos on the fly. So whenever the user it clicks on the view button or the play button, we will transfer it then and there. Okay, so next we looked for most frequent video types that are actually streamed. So we found out that MP4 video files has a broad support to play natively on most devices. So we could prioritize the transcoding .mov videos and fall back to native support for MP4 and transcoding as a first. So with some data analysis, we decided to run video transcoders asynchronously. So we could prioritize transcoding .mov videos and fall back to the native source for for watching the MP4 extension files when transcoding hasn't finished it. So with some data analysis, we decided to run video transcoders asynchronously after an upload or shareable link creation and build an SLA. Okay, so problems and solutions. Breaking down the problems and solutions. Breaking down the problem of delivering video streaming to our users, we build a pipeline. Let's upload the video, notify the transcoders that the video needs to be transcoded into a native supported video format. So which okay, so let's and then we like transcode the videos and store the transcoded videos and stream the HLS or the CP later. So uploading and storing last video. So Ignite object store always does this well. We have petabytes of content, including videos stored by our users. So the YouTube uses this Ignite, okay, EGNYT Ignite object store, right, for storing the large videos, which are in terms of petabytes, which is indeed like a huge collection of videos. Then notifying the transcoder job. So as soon as a video file is uploaded by any channel or publisher, so we want to notify it to the transcoding team, or basically transcoder, that your job needs to get started. And we need a good messaging system. We were already using the RabbitMQ, Redis, PubSub model, and Scribe, but this use case was different as we wanted video transcoders to be deployed anywhere in the world. This could be in an Ignite managed data center. This could be in an Ignite managed data center or within public clouds to scale up for load specs. This meant we needed a global messaging system such as Google PubSub, or Azure Service Bus to modify transcoders when a new file is uploaded. So using a messaging bus came with its own set of challenges. Your transcoding can Okay, so this means that this could be in an Ignite managed data center or within public clouds to scale up for the load spikes, which you could get by right, increasing the by increasing the viewers count. And this means that we need a global messaging system, so the Google PubSub model and the zero service bus to notify the transcoders. So using a messaging bus built so using a messaging bus comes with its own set of challenges. Video transcoding jobs can run for hours and we needed to be able to follow this. So using a messaging bus comes up with its own set of challenges. Video transcoding jobs can run for hours and we needed to be able to hold these on a message during this time. While transcoding, the message bus should not deliver the same message to another plan, so we needed long list. For example, we started with because while transcoding, the message was should not re-deliver the same message to another client. So we needed long list. For example, we started with the latest Google PubSub client, but had to go to using a previous version since the latest one would not allow us to renew the lease. We are transcoding, so this is a problem. Okay. For example, we saw the latest Google PubSub plan, but had to revert to using our previous version since the latest one would not allow us to renew the lease for a longer duration. Okay, let's move on to the next topic, which is like video transferring. So this is a difficult problem to solve at scale, right? Our first attempt was to see if we could outsource video transcoding to a partner. So we could outsource the video transcoding to a partner with an off-the-shelf product. Okay, so, but the cost. So this is a difficult problem to solve at scale. So our first attempt was to see if we could outsource this video transcoding right service to partner with an off-the-shelf product, but the costs were too high. In fact, our analysis showed that it was 90% cheaper to run the video transfers in-house. I don't know what that means in detail. So this led us to the conclusion that we would need to roll up our sleeves and build the in-house for both the compliance and the cost reasons. So this led us to the conclusion that we would need to roll up our sleeves and build the in-house for both compliance and cost reasons. To transcode a video in HLS. So to transfer the video to HLS, we choose FFmpeg. FFmpeg is a collection of libraries and tools to process. So FFmpeg is a collection of libraries and tools to process multimedia content such as audio, video, subtitles, and related metadata. FFmpeg is by far the best free software available to transcribe. Transcode video to HLS. This will be live streaming, which was FFmpeg as a collection of icons. So I think where this is way for the best free available software for transcribing videos, and it has a very good HLS. FFmpeg can easily create the various HLS segments at different resolutions. After detailed testing, we choose the following MPEG command. Uh, okay, so FFmpeg is by far the best free software available for transferring videos, and it has very good HLS support. FFmpeg can natively create the various HLS segments at different resolutions. Okay, so our video transcoding job outputs the following files: stream.m3ua. Master playlists contain the list of all resolutions and playlists that Ignite supports and their bandwidth recommendations. So resolution dot m3 freeway each resolution supported. Okay. So resolution dot m3 u8 for each resolution it's supported with Ignite and the setting stream dot m3 u8, for example 614 to 480 480 pixel dot p dot m3 u8 is generated visual playlist for the specific resolution. So then video segments are smaller fixed time segments times video segments time to video segments for each of the resolutions supported. Unlike asterisk at m3 u8, files. They are actually video files and not metered files. I think we have a lot to read, so I'll just go through a bit faster. So yeah, so video transcoding job right outputs of following three files. First is a stream.m3u8, which is basically a playlist. It playlist a container or a folder, you could say, which lists or which stores all the resolution and playlist, right? Like night supports and the bandwidth recommendation. Inside this, we have like resolution .m3 fluid resolution can dynamic depending on the quality of the video. So it could be 240, 144p, 240p, then yeah, I guess 360p, 480p, 720, and so on and so forth. So these are the actual resolution. Then within that we have like subsegments, right? We have video transcoded files of the subsegments of sub-media segments, you could say. So a small sample generated in 3 weight file as follows. Stream is like this, voltage is like this. So scalability. Okay, so the next big challenge we need to solve for scaling the video transcoding jobs on demand. So runtime of video transcoding jobs are very smart. The next challenge we have is to solve. We have to solve is scaling the video transcoding jobs on demand. So runtime of video transcoding jobs are very asymmetrical, meaning jobs processing smaller videos could finish quickly, but larger like jobs could take an hour, bring up another. So runtime of video transcoding is very asymmetrical, meaning jobs which are processing smaller videos could finish up quickly, but larger jobs could take time, like going up to the. So it was clear to us at the outset that we needed to deploy a video transcoding jobs on a platform that could adjust dynamically based on the current backlog and seasonality. Our first preference was to leverage. So it was clear to us at the outset that we needed to deploy video transcoding jobs on a platform that could adjust dynamically, right, based on the current backlog and seasonality. So our first preference was to leverage a serverless architecture for deploying the video transcoders. Okay, so we will basically put our video transcoders on a serverless architecture, maybe an AWS architecture, and then the video transcriptors would do their job. So we like this idea that we could build this on cloud functions, scaling automatically, right, without worrying about the backlog and the load spikes. However, we soon realized that it was too early to leverage these services at scale. Video transcoding is a CPU intensive task or an operation and needs specific hardware like dedicated CPUs or even GPUs with enough memory and So video transcoding is of course a CPU intensive operation and needs specific hardware like dedicated CPUs or in GPUs with enough memory and native FFmpeg installed on it. So it's challenging to build this on a serverless, and we determined that Kubernetes suited us better. So we created Alpha and Docker containers of FFmpeg plus Python, deployed these within Kubernetes. Plus, since we already use Kubernetes within Ignite, there was a small learning curve. We found that video transcoding jobs run faster on GPUs, but this isn't cost effective. The best trade-off. Found out that video transcoding just run faster on GPUs, but does doing this isn't cost effective, of course. So the best trade-off between speed and cost was allocating 4 CPUs to each video transcoder jobs. The best trade-off between speed and cost was allocating 4 CPUs to each video transcoder job. At 4 CPUs, we were able to process videos at about 25 to 40% of the video playtime. Yes, and a 1 hour video would take about 25 minutes to transfer. Adding more CPUs to a video transfer job did not produce linear benefits. So it was best to stick to 4 CPUs per job and instead provision more jobs. So for uploading a 1 hour video, it would take around 2 minutes just for transcoding. So adding more video CPUs to a video transcoder job did not produce linear benefits, so it was best to stick to 4 CPUs for job and instead provision more jobs. We deployed custom metrics based on scalars mm, which would look where is that? Which would look at the current backlog in the video transcoding queue and deploy more jobs as needed. Autoscaler would reduce the number of jobs when backlog was down. Autoscaler is the most important part of managing costs and user expense. Without Autoscaler, it's impossible to provide a good transcoding SLA without provisioning and thus escalating costs. Transformers have one more challenge. They can get stuck every now and then. Solve this we have built. Okay. Transcoders have one more challenge, so they can get stuck every now and then. To solve this, we have built-in health monitors to in our transcoder Docker containers. If the health check fails, its cluster restarts a container. Determining if a transcoder is stuck is not easy. We have a few cooks around. We fail the health check if the transcoder hasn't received a message from the messaging bus topic for a while, and then there are still outstanding. Okay, before the health check, the transcoder hasn't received any message from the messaging bus topic for a while, and there are still outstanding messages in the topic. Okay, let's read this again. I didn't get it actually. We failed the health check if the transcoder hasn't received any message from the messaging bus topic for a while, and there are still outstanding messages in the topic. It failed the health check if the FFmpeg was struck that it's not producing individual segments but it's still running. Restarting a transcript puts a message it was holding back into the backlog after the lease expires and gets picked up by the next available transcript. Deployment of the service also needs to be optimized for the targeted public cloud while building this. So, deployment of the service also needs to optimize for the target public or cloud while building the service level cloud for preemptible nodes in GK equals kth cluster. I don't kind of get what's written because there are many things which are very new to me. Preemptible nodes are cheaper than regular ones. The downside being that they can reach certain ones. Okay, so in the transfer videos, so as seen above, transcoding is a very expensive operation as it makes sense to store and retain the transcoded objects or the videos files for some reasonable amount of time depending on the video quality uploaded. Transcript videos could be anywhere from 20% to 50% of the original size. At our scale, this is also an interesting problem. We need a long-term storage option for the transcript videos, one that is durable and okay. So we needed a long-term storage option for the transcript videos, one that is durable and scales to handle petabytes, right? It should be durable and it should be able to handle right large. Um, so basically, for the backup, so it's kind of backup like for the transcoded videos. After the videos are transcoded, you need to store it somewhere, right? We don't want to right do the transcoding or the video transcoding for every user or for every viewer. So once the video is transcoded, it's served to every other object, so every other viewer. So once object life could be variable in some cases. Okay, so we need a long-term storage option for the transcoded videos, one that is durable and scales to handle pyramids. Object life could be variable, right? In some cases, it could be for a few days, but in most cases, it would be for months. To solve this problem, we needed something we termed as derived object store. An object store that would store derived objects like a transfer videos. The life cycle depends on the object life could vary, so in some cases it could be for a few days, but in most cases it would be for months. To solve this problem, we need something we termed as a derived object store, an object store that would store derived objects like a transcoded videos whose lifecycle depends on the primary object uploaded by the user. Availability will be a bit relaxed, but availability will be a bit relaxed. At the time, our core object rich store did not support storing derived objects, but we were already scaling it to billions of objects and petabytes of data. We knew how to manage it and manage it well, and it was perfect place to store transparent objects. So we went with the right about adding the derived object store feature to our core object store and solve one more piece of transcoding puzzle. Like, and finally we have to do the survey or serving the transfer videos to the viewers. So serving streamed videos to users is different from serving API or web UI request. Video segments are usually larger and okay. So video segments are usually larger and long running and can result in sudden bursts when videos go viral. So considering the unpredictable nature of the video request, right, so any videos can go viral. So once video goes viral, so it is more in demand and more users, right, or viewers are willing or trying to right, hit the API so that they can watch the video. So considering the unpredictable nature of the video request, we decided to keep videos serving completely isolated from our regular traffic. Okay, a video service is based on OpenREST with all the authentication and video discovery returned in Lua. We deployed our video service with a cache on a dedicated infrastructure fronted by dedicated domain name. This is media.ignite.com. This video service did not share any infrastructure components like firewalls, switches, and ISP links with our primary services, which allows us to scale the video service and rate limit users purely on our video needs. Since video service nodes were mostly doing authentication, authorization, and serving doctors. Okay, OpenDST. To start a driver with this by deploying two containers along with the video service. OpenDST in the video service pod in Genix. Prometheus exporters. Export in Genix metrics to Prometheus, a monitoring tool. Something like that. Okay, export Prometheus metrics to stack driver. Once we had the active connections metric in stack driver, we deployed a custom metric HP to scale up video service pods when active connections increase. Finally, and put together, this is how our overall algorithm looks. So Ignite Data Center. Okay, so we have this content creator which will upload and share the video online, make it public. So after this, we have like something called the object store manager, and we have to have a pop sub notifier which will notify to all subscribers, right? So all scalar transcoders, which service is a different service altogether, not a scalar. We use local copies, we use remote copies, transcripts. Okay, monitoring. Monitoring is a key to any production scale system, and transferring some videos is no different. There are several things to monitor, and we do that using it to use our transcoders and mine stats of other components like offset topics. And video service OpenDST service From a transcoding perspective, the key metric is to measure is the backlog, as this directly affects our squeezes. We monitor the number of messages outstanding in the PubSub topic at any point of time. If there are too many messages in the queue waiting to be processed, Autoscaler adds more transcoders as seen below. As the number of outstanding messages increases, we increase the number of transcoders. As the backlog comes down, we reduce the transcoders. Our research teams also get notified when the backlog is beyond certain threshold and the Autoscaler is not able to keep it up to it due to the max transcoders. Limit exceeded, SRE that then makes an informed decision if our scalar limits needs to be bumped. We monitor transcoding speeds and transcoding lag that helps us for the user experience. We monitor videos process as well to understand their traffic patterns and costs. This is how we solve a long-standing problem of streaming videos across devices to our users in a cost-effective and compliant way. The next phase in this project is finding the best way to have a high performance transcoding of videos on the GPUs in real time for recently uploaded videos to serve them immediately. So this is all for today. Let's meet tomorrow. Good night. Have a safe and sound sleep. Goodbye.